Allora, buongiorno a tutti o buonasera, quelli che sono in Italia. Oh, sorry, I should speak English, right? You said, I guess, sorry. Okay. All right, so welcome to this symposium. I'm Giorgio Gratta from Stanford University. I'm one of the co-chairs of the selection committee, and the other co-chair being Patrizia Rossi from JLab. And we also have Emilio Nanni from Slack with us, who's actually been part of the selection committee. So I think in general, we've been very impressed by all the candidates, and of course, even more so by the three who ended up here. So this is the final symposium for the 2023 Bruno Touschek Young Investigator Award of ISNAF. And this is essentially an award that is sponsored by INFN. And the award is essentially in physics or physics of fundamental things in some sense, which includes astrophysics and some of the condensed matter physics that is represented here, and of course nuclear and particle physics. And I don't think I have time to say more, but Bruno Touschek was a very distinguished physicist, actually active mostly in Rome, as far as I know, but in fact he essentially is credited for inventing or developing E plus E minus collider, in particular ADA e Frascati, which stands for Anello di Accumulazione, is I have to say in Italian. Okay, so I think with this introduction, I hope I haven't forgotten anything. I can introduce the three finalists, Sofia Fatigoni in alphabetical order, Sofia Fatigoni from Caltech, Simone Mazza, who is at UC Santa Cruz, and Chiara Trovatello from Columbia. And so I don't think I need to say anything else. Oh, sorry, I need to say that Patrizia and I share tasks, and I've done the introduction here, and Patrizia will be at the embassy for the prize ceremony. What is it, in 2 weeks? I am too far and I cannot come, so this is actually, this works well sort of this way. Okay, so I think unless I'm forgetting something, and let me know, otherwise I think Sofia, you can start.
Okay, so I'm gonna share my screen. And then I'm gonna start. Okay, so hi everyone. I would like to start by thanking you for having me here today and for giving me the chance to show you what I've been working on in the past few years. My name is Sofia Fatigoni. I'm an experimental cosmologist and also a postdoc at the California Institute of Technology. And for the past few years, I've been part of the BISEC experiment, which consists on a series of telescopes observing the microwave sky from the South Pole. In particular, I've been focusing designing, building, testing, and deploying the BISAP array, which is the latest stage of the experiment. But I will talk more about this in a moment. So I would like to start this talk by giving you an overview of what is the science case for BISAP array. Then I will introduce the architecture of the experiment and my first contribution to the experiment, which is on the hardware side. Then I want to talk about my second contribution to the experiment, which is more on the data analysis side and consists on a new method to subtract atmospheric foregrounds from our cosmological data. And finally, I will give you an overview of what is the deployment status for BISAP array. Okay, so let's get started with a little bit of cosmological context. The inflation theory states that the universe began with a very brief period of exponential expansion, about 10 to the minus 35 seconds, that would have transformed the universe from being an infinitely dense point to being a finite volume. If inflation happened, what to expect to find in the primordial universe is a background of primordial gravitational waves. These gravitational waves would be too faint today to be detected with a standard gravitational waves interferometer, but we have a chance to detect them indirectly. And to do this, we want to use a tool that is very popular among cosmologists, that is the Cosmic Microwave Background, or CMB. The CMB is basically the oldest picture that we have of our wide universe. It's an image of how the universe looked like 14 billion years ago, in the first moment in which it became transparent to radiation. So before that, the universe was opaque. So anything that happened before that, we cannot see directly. But we have a chance to measure what happened before that by the imprint that it left on the cosmic microwave background. This is the reason why the CMB is such a powerful tool. So if inflation happened, we expect to find in the primordial space-time two kinds of perturbations: scalar perturbations, which would have been generated by fluctuation in the density of matter in the primordial universe, and tensor perturbations, which would have been generated by primordial gravitational waves, so by this background of primordial gravitational waves. These two kinds of perturbation would have created in the polarization of the CMB two very well-distinguished patterns. One pattern that is parity even and is also known as E modes, and another pattern that is parity odd and is also known as B modes. And the particularity is that while E modes can be generated by both scalar and tensor perturbations, B modes can only be generated by tensor perturbations. So an evidence for B modes in the polarization of the CMB would be direct evidence for this background of primordial gravitational waves that inflation would have produced. Today, there is still no evidence for inflationary B modes in the CMB polarization. So to constrain inflation, usually we make use of two parameters: the tensor to scalar ratio, which is the ratio between the amplitude of tensor perturbations and the amplitude of scalar perturbations, and the spectral index for scalar perturbations. The reason why this parameter space is so informative is that different inflationary models put different constraints in this parameter space. For example, here you can see the three black lines which correspond to different inflationary potentials, and also the shaded pink line correspond to another inflationary model. So putting a constraint in this parameter space means deciding which inflationary models are acceptable and which ones are just to be ruled out. In this plot, you can also see two posterior distributions from two datasets. So in green, you can see the posterior distribution from all the CMB datasets, basically before BISEC-KEK. And in blue, you can see the same what happened to the same posterior once we add the latest set of BISEC-KEK data. So you can see how much the posterior shrinks in the direction of R. And you can also notice that by doing this, basically, we rule out all the inflationary models plotted in this graph. So the BISEC-KEK experiment has been having for the past years the best constraint on inflation. And this result was achieved with the previous version of the experiment for a total of 4,000 detectors on Sky. Once fully deployed, BISEP array will have a total of 20,000 detectors on Sky. So this is to give you an idea of the level of improvement in constraining inflation that we plan to achieve with BISEP array. But how are we planning to do this? So now I want to talk for a moment about the architecture of the experiment. So once fully deployed, BISEP array will be composed of 4 receivers observing the sky at different frequencies in the range from 30 gigahertz to 270 gigahertz. Each receiver is a custom designed cryostat, where the focal plane is located on top of a sub-Kelvin structure. And 12 detector modules are tiled onto the focal plane, which is kept at 250 millikelvin. Each detector module contains a detector tile, which is basically a matrix of pixels, where the number of pixels varies from 16 to 700, depending on the frequency. Each pixel contains itself two detectors, which are sensitive to orthogonal polarizations. So as I mentioned, we are interested in measuring the polarization of the CMB. So we want each of our pixels to be a polarimeter. And finally, each detector is a TS, that is transition edge superconductor bolometer. That is basically a superconductor that is kept in its transition region in between the range of temperature in which it is superconducting and the range of temperature in which it is normal. The transition region is the region where it is maximally sensitive and where it actually behaves as a detector, because to a small change in temperature, it corresponds a big change in resistance. So these huge matrices of pixels are multiplexed in time domain and read out using the multi-channel electronics. For the two bicep array high-frequency receiver, which host on the focal plane the largest number of detectors, a redesign of the readout electronics was necessary to be able to read out a highest number of detectors. So this is my first contribution on the hardware side and my main contribution on the hardware side to the experiment. I have designed the double MCs, which is basically a new version of the MCs that is able to read out twice as many channels in a single subtract. So I have designed the double MC, I built them, tested them, and they have been deployed at the South Pole in December of last year. Now I want to move to talking about my second contribution to the experiment. So if we want to observe the microwave sky from the ground and not with a satellite, we need to be very careful because the microwaves are very sensitive to the atmosphere. Or to say it better, actually, the atmosphere is very sensitive to the microwaves. So if we want to observe from the ground, we need to be on a site that is at high altitude and is very dry. So it's basically a desert. The South Pole is the best site on Earth because it is a high altitude and is the driest desert on Earth. In addition to this, we also want to be smart about where we put our observation bands. So we want to put our observation bands in regions, in the so-called atmospheric windows, that are basically regions of the atmospheric spectrum in which the transmittance is maximum. But this is not enough because the signal that we want to detect is very, very faint. So the level of systematic control that we need is very, very high. So in 2016, a water vapor radiometer was deployed at the South Pole next to the bicep Keck telescopes with the goal of doing site characterization. Well, I found out that this can be used to do much more than this. This water vapor radiometer is basically a spectrometer that observes the sky in 4 frequency channels centered on the 183 gigahertz waterline, and it continuously scans the sky in azimuth at an elevation that matches the center of our CMB maps. During my PhD, I've decided to look for the first time into the data acquired by this water vapor radiometer to build a pipeline for systematic modeling and correction, and then to use this data in correlation with our data to remove atmospheric noise. So what I'm showing here is a map from water vapor radiometer data at the bottom. So basically here you have on the y-axis the azimuth direction on sky, and on the x-axis time. And this is the precipitable water vapor extracted from a fit on this water line for each point, extrapolated to sky brightness at 270 gigahertz to match the Keck receiver considered in this plot. On top, you have basically what the Keck 270 gigahertz receiver is seeing in total power at the same time and in the same region of the sky. So in our standard pipeline, the atmosphere is removed doing a third-order polynomial fit and filtering in the azimuth direction. So this method actually removes the atmosphere. The problem with this method is that it also removes all the large angular scale structure from our data, which is not what we want, because by doing this, we lose a large fraction of our data and at large angular scales, which are very precious. So I've decided to take an orthogonal approach and to basically fix myself at a given azimuth and look at what happens in the very long time scales. And not only what happens on the CMB dataset, but also what happens on the WVR dataset in correlation. So here on the right, you can see the 2 time streams corresponding to the blue line. The blue line is the water vapor radiometer, and the red line is the Keck 270 GHz receiver. You can see both from the maps and from the time streams that the correlation is very good, which means that basically most of our total power data come from atmospheric brightness, just to give you an idea of the issue that the atmosphere is. Even at the South Pole. So the new method consists on the following steps. Basically, I fit to each of these 2 time streams a 12-order polynomial model independently. Then I find a correlation factor between the 2 models by doing a linear fit. And finally, the clean dataset is going to be the starting dataset minus alpha, which is the scale factor, times the WVR model. And this is the result. So on top, you can see the map before applying any kind of filtering. At the bottom, you can see the map after the standard polynomial filtering. And in the center, you can see the map after applying my new WVR-guided filtering method. What I want to point out here is that the noise level achieved in the second and in the third map is actually very similar, which means that the 2 methods two methods are equally good in removing atmospheric noise. But you can see the difference in this other plot. So this plot is the square root of the power spectrum for these three maps. So in blue, you have the starting data set. In orange, you have the dataset after the standard polynomial filtering, and in green, the dataset after the new WVR-guided kind of filtering. So here it is very clear that by using just the blind polynomial filtering, we lose all large angular scales. So we lose all information in these angular scales. While by using the new WVR-guided method, basically we still remove atmospheric noise because this bump at low frequency just goes away, but we keep all the rest of the information. So this method is very promising in making us recover more modes in our CMB power spectrum constraint, and by giving us the ability to have information on larger angular scales. And the large scales modes are very important in constraining inflation. So this method is very promising in helping us pushing down the lower limit on R.
2 more minutes to go.
Finally, I want to close this talk by giving you an overview of what is the status of the deployment of bicep array. So the first bicep array receiver was deployed at the South Pole in between 2019 and 2020. It was the 40 gigahertz receiver, and it had a total of 800 detectors on the focal plane. We deployed a full focal plane, and I was part of this deployment. And the second bicep array receiver was deployed at the South Pole last year. I was also part of this deployment, but it was deployed with a partially populated focal plane. Once fully deployed, the second bicep array receiver will have on the focal plane a total of almost 8,000 detectors. So I'm leaving again in 3 weeks for the South Pole to complete the deployment of the focal plane of the second bicep array receiver. And with this, I'm gonna end this talk. Thank you very much for listening, and please, now I'm gonna take any question.
Okay, thanks a lot. Since there's some questions, I think there's few of us, so we can just, I don't think we need to raise hands.
Okay, I raised my hand, but
oh,
okay.
Sorry, I cannot see it. I'm actually very clumsy with those things.
Okay,
So
doesn't matter.
Speak up.
Okay, so I can start with my question. Okay, first of all, thank you very much for this clear and very interesting presentation. I have 2 questions regarding your contribution. The first one is in English. Yes. The first one is you don't have the number of the slides, unfortunately, but is not the previous one. May you show that one? Yes. So okay. This is a new, very interesting results indeed. Where my simple question is. Do you know if some other groups or collaboration are using this method or they plan to use it?
So I think this is the first time that this method has been I came out with this method, so this is the only collaboration that is actually trying to use this method, although there are still some problems that are more related to the instrument than to the method. For example, the water vapor radiometer is not reliable 100% of the time. So we cannot rely on this method for the full coverage of our observations. Well, I would say that this is the main thing. I know that there are other groups, even in Chile, that are interested in getting a water vapor radiometer to try to do the same. But as of today, we are the only ones who have a scanning water vapor radiometer, and the only ones who are trying to do this.
Yeah, indeed, the Chilean group was indeed in my mind when I asked the question. The other, if I have time, if I make the second question, is regarding your hardware contribution. If you can go to the slide with, yes, this one. So you said that you have designed and then constructed and then built the new electronics. Design starting, I assume, from the initial. So what exactly what was the major contribution on this?
So the standard design includes half of these cards. So first of all, this is a mechanical redesign in which we compacted the subract to be able to host more cards. And then we basically rerouted signals on the backplane to be able to match that. This is basically what I've been doing. Also, we have redesigned these filters here so we connect to the cryostat using these connectors, and then the filters are routed through these flexes back to the focal plane. And we had to adapt this design to be able to do this in this new version, because in the old version, the design of the filters and the location of the filters in the filter rail is different. And also by doing some impedance matching with the rest of the readout electronics inside the cryostat, with these electronics, we are actually able to multiplex faster. This is the other part of it.
Okay, thank you.
Emilio, Eugenio, tell us when we're running out of time, right? Emilio, maybe.
Most definitely.
Okay, Sofia, thank you for the very nice presentation. I wanted to ask if you could go to the slide where you show the spectrum that is observed for the water vapor. It was centered around, like, yes, this one here. I wanted to ask in the water vibrometer, what sets the spectrum that's seen by each of these channels? And then the kind of the follow-up to that is, are there ways that you can improve the sensor so that you get better measurements of the impact of water on your recording?
You mean how we could do smallest bandwidth, so having more than 4 measurements? So well, this is
first, yeah. First is what's limits that, and secondly, what could you do to improve it?
So this is an IF intermediate frequency heterodyne receiver. So it measures in these 4 frequency channels, because really this is all we need to fit the shape of the water line. So I don't think that by having more channels or channels like that are distributed differently, we can improve a lot the quality of the observations. We could make it, for example, polarized. There are other things that we can play with, because actually the other part of it is that, so we have evidence for part of the atmosphere being polarized, probably due to ice crystals in the atmosphere at the South Pole specifically. So this is another thing that we would want to study in the future, and we still don't know how well this correlates with the actual precipitable water vapor. So in order to be able to make these observations more precise and correlate them in a different way to our data, like doing a step forward in this method, I would say we could make this polarized, or we could make it a cold receiver to lower the noise. But I wouldn't actually change the channel distribution, because I play with it quite a lot, and that's actually pretty good. So there are other things that we can improve for sure, even like the model that we use, the atmospheric layers. But all these things are more like related to the way in which we model the atmosphere than how these channels are distributed in frequency.
Thanks.
Okay, if we still have time, Eugenio, I also have a short question.
Yes, sure. There are 5 minutes more.
Okay. So again, Sofia, thanks a lot for the really nice presentation in general. And sorry, I'm actually sort of stuck on the radiometer simply because I don't know exactly what this is. So I wanted to actually, confess my ignorance. And so is this just a passive thing, or do you make like some sort of light? Like say with some, no, I guess you cannot make some artificial star kind of thing. So how is it different from your receiver? Essentially, that's my
completely.
No, well, okay, but then what's the property? So what is it that you're looking at to measure the transparency or the opacity versus what the CMB detector does?
So basically, okay, I think that what is confusing actually is this one, because here you see 2 maps at the same frequency, right? So the thing is that there are, to get to this, there are many intermediate steps. So what I start with is these 4 measurements at 4 frequencies that are literally around this line. So to these four measurements, I fit the shape of the water line, assuming some atmospheric model that could be arbitrarily precise. I use a 30 layers atmospheric model taken for a specific day to which I costume the temperature of the lower layer, so it's arbitrarily complicated. To this, I extract just a value for the precipitable water vapor. Actually, I have another slide that I put at the end that maybe I can get to, in which I have the intermediate steps. So these are the 4 maps in the 4 frequency channels, just in what, like, showing what the radiometer is seeing. Then from each set of 4 points corresponding to 1 pixel in this map, I extract through the fit a value of precipitable water vapor, and I make a map in precipitable water vapor. At this point, I use, again, an assumption on the atmospheric spectrum to extrapolate to what the atmospheric would, so to the temperature brightness of the atmosphere at any frequency that I want. So in this slide here, I'm showing the the correlation with the 270 gigahertz, and so here I extrapolated to 270 gigahertz. But I can do this at really any frequency because I'm just using information on this. So given a precipitable water vapor value, I can basically plot the full spectrum of the atmosphere and then just integrate in the bandwidth that I'm interested in.
Okay. So, but essentially the point, sorry, again, this is because I didn't know anything about this, but you deliberately go to a place where the atmosphere absorbs a lot and use that to measure how much absorption there is there. But then you have to rely on this model of the atmosphere to extrapolate to your bands where there's very little absorption. Okay, all right, good.
Yeah.
Thank you, yes. And what's the systematic? I mean, how reliable is this model? Particularly when you go very far in frequency from your what is it, 170 something?
So the model, the model is pretty reliable because I use also, for example, MERRA data to tune the atmospheric temperature and pressure in some layers day by day. So the model is pretty good. The systematics that I was talking about are more related to the instrument. For example, the instrument is, so it's very hard to put something on ice without having it tilted. So the instrument is slightly tilted. And so every time that it scans, basically there is a sinusoidal that we see in our data that we want to remove, but making sure that we don't remove anything else. So what I've done is basically fitting these for years and years and extracting a tilt, like a tilt and a trending tilt of the building. And then I remove these from each of the data that I take. Also, in addition to this, there is another signal that has twice the frequency that we are still trying to understand where it comes from. We have some ideas, but we are not fully sure. And also, like, I've been studying this to understand how stable it is and how we can remove it to the data without, again, impacting the data set.
Okay, thanks. That's very clear.
Okay, I think we are running out of time. This is Eugenio. And moving on to the next speaker, which should be Simone Mazza.
Okay.
I'm going to stop sharing.
Thanks again, Sofia. Simone, the floor is yours.
All right, let me share. Will be coming up. All right. Go full screen in some way. Oh, yeah, this is fine. All right. So yeah, thanks for the opportunity to present this seminar event today. So I'm going to talk about innovative sensor development for particle physics, nuclear physics, and beyond. So first, a little parenthesis about me. I'm currently an assistant project scientist at SCIP, University of California, Santa Cruz. And SCIP is the Santa Cruz Institute for Particle Physics. And I was a former postdoc there. So I'm working on algal radiation harness R&D for the HDD subdetector in the ATLAS experiment. I'm leading the design of the silicon active target for the Pioneer experiment. I do R&D on AC algats for the electron-ion collider, which is going to be at BNL in 10 or so years. And on the side, I also do blue sky silicon sensor R&D. So first, a small summary of the talk. The first sentence is a bit provocative, which is the current HEP research, high energy physics research, is kind of in a standstill. That's because after we discovered the Higgs boson at LHC a few years ago, the standard model is complete. You can see all the green check marks. But we know that something is out there because there are several observations that indirectly contradict the model, like hierarchy problem, dark stuff, matter-antimatter symmetry. So we know that there is something extra to the standard model, but there is no clear way to discover it. So one upcoming challenge, that's the first topic near future, is the high luminosity LHC, where we increase the luminosity of LHC times 3. And I'm gonna show how this is an example of how innovative technology can help push the limit of discovery. But however, at high luminosity LHC, we expect no big discoveries. At most, we expect to observe the Higgs in the dimuon and the Higgs interaction. So is there really nothing new to search for? Well, in fact, we are kind of entering an era of experimental-driven discovery, where we kind of probe the standard model in several different ways, putting cracks in it until we find out that there is something really wrong. So the immediate need at the moment is to build all this kind of small-scale experiment to probe the standard model. And in particular, I'm going to talk about the Pioneer experiment that studied the lepton flavor universality violation. And this is the second topic. And then the third topic is the far future. So in the far future, we need to build next generation of colliders. First Higgs factories, then something like 100 TeV hadron colliders. And it's not clear what the next community step will be, because we probably gonna have only one collider per type, and we need to choose wisely. So the development of dynamic technology for these new frontiers is critical. And a thread connecting all of these topics is exactly the technological development. So near future, as I said, we are gonna go to high luminosity LHC. We increase the pileup, but this means that a lot of tracking detector in high luminosity LHC, they're going to start to lose performance because you have much more particles. So a way to mitigate this is to use timing for the tracking. So it's XYZ plus time. And there is an example here. So you see all these points. These are tracker hits. And it's kind of hard to say, okay, this is one track and this is the other. But then if you assign a time to each point in the track, then you can easily say, okay, this track is these points because they are at the same time. So to do this, we use low gain avalanche detector, which are thin silicon detectors with internal gain. And this is a perfect example of what started as a blue sky R&D in one of the R&D collaboration at CERN, and then in the end was used in an actual experiment. With this sensor, you can get a time resolution of less than 20 picoseconds, which is pretty impressive, and you can do this for tracking trick. In a few years ago, both Atlas and CMS submitted TDRs for large-scale timing upgrade, and I was heavily involved in one of the two, the Atlas one. In fact, I was main editor of the TDR. For this kind of detector, the big challenge was the radiation hardness. And we had an extraordinary technology development in just a few years. So these sensors, these ALGATs, are super good when they start, where they're new, but then when they accumulate radiation damage due to an effect called acceptor removal mechanism, the gain starts to go down, so you have less collected charge and time resolution gets worse. So after years of R&D, testing sensor, collaborating with companies, we found out that the radiation hardness can be improved by changing the gain layer profile, adding carbon in the gain layer, or putting the gain layer more deep. So the combination of all of these techniques gave us the sensor that we needed, which were radiation hard up to 2.5 times to the 15. However, after this development, we still have big issues because these sensors have low granularity, they have high power dissipation, and it's a problem to go to extreme fluencies. So now we go to mid-future. I'm going to talk about the Pioneer experiment, which is a next generation or pion decay experiment that is going to take place at PSI. And the plan is to have a phase 1 to improve the measurement of the charged lepton flavor universality RMU by an order of magnitude in respect to current measurement. So you can see the plot here on the right. The current best measurement is from pi nu, and that's the blue line. And this is in orange is the theory measurement, the theory calculation. And our goal is to basically reduce this error bar to the point that if the mean value remains where it is, you are going to have a clean, basically lepton flavor universality violation. Then on phase 2 and 3, we plan to measure the pion-Beka decay branching fracture very precisely. And this is an important test to the CKM universality because it's a very clear measurement of EUD. In this detector, we are going to have 3 main detectors, an active target of which I'm heavily involved in, a calorimeter, and a low mass tracker in between. The active target is going to be a high granularity full silicon active target with timing capabilities, basically a very compact block of silicon. And for this active target, the chosen technology is again LGATs because they have higher signal to noise, fast full collection time, and great time resolution. So the idea of the experiment is pretty simple. You measure the energy spectra of pi nu and pi mu nu. So in one case, it's 2 body decays. In the other, it's 2 subsequent decay. And in the end, you have a 4 body decay. So if you look here, one of the 2 is a very peaked spectra around half of the mass of the pion, while the other is what we call the Mitchell spectrum. So in the past, you just measure the energy of the positron in the calorimeter and cut in this point. However, if you really want to be precise like we want to, you need to take into account this tail. And this cannot be measured in the calorimeter. So what we do is we use the ATER. And in the ATER, it's so granular that you can actually see the pion coming in and going out as a positron, like in this first event here. Or if you have in the middle muon decay. So first you have a track, then you have another hot track, and then another track. And this is, of course, gets more complicated if you have decay in flights. So this is something that we need to study very carefully. So the challenges for this extraordinary piece of technology is that we need to recognize it. There are just a few nanoseconds apart with very high spatial granularity, with good energy resolution on the heat, low material all around, large dynamic range because you have pion and muons that deposit a lot of energy and the positron that deposit just a small amount. We also need to be very compact with very small blind regions, and we are going to need a very complex triggering scheme. So now I switch topic again and go into the far future. So we made a wish list in the US a few years ago that is called Basic Research Need. And we said, okay, we need 5 micron spatial resolution, 10 picosecond temporal resolution, low material budget, and low power consumption. So at the moment we are here, Illumina LXC with good LGAD devices. So we need to go to small experiment, then to X factories when we need 10 picosecond, 10 microns, and low pileup. But then we also need to build something for the next generation hadron collider where you need all of these requirements, but in a high pileup and high radiation environment. So for the first step, where you just need a high position resolution and high time resolution, we can use this new technology that was actually patented and developed at UC Santa Cruz, which is AC coupled LGADs. The idea is that instead of segmented the top, you AC couple it. And the collected charge is shared between electrodes. So it's a new concept of a tracker where instead of having a very granular standard tracker, you have a more sparsely granular tracker where you combine the output of all the channels to recognize where the particle hit. And at the same time, you can have the very good properties of LGAD, so high time resolution, etc. And this is really good for the electron ion collider, for Pioneer. For the X factories, we probably need some technological advancement, but it's possible because it's all a low pileup environment. However, we need to develop completely new technology for future colliders where you have a high radiation hardness and high occupancy, like FCC-HH. So we need at least an order of magnitude increase in radiation hardness and at the same time higher granularity. And you can see in these two boxes at the bottom on the left, a lot of different ideas how to port this technology to high granularity, and I'm actually one of the inventors of one of them. And on the right, how to try and push the radiation hardness of these devices. So there is this critical need to continue developing these sensors if we need to apply them for far future application. But at the same time, we also need to work on lower power electronics. And this is what we have been doing at UC Santa Cruz. Have been collaborating with these new companies to basically, with this company, there is also another one, to develop a low power electronics for high timing application. But we also need to think ahead because, for example, FCC is going to be 50 years. So maybe we're going to have completely new materials. So diamond, silicon compound like silicon carbide, where you have a higher band gap. So maybe you need gain inside to have the same level of response from positrons and electrons. Or at the moment, they're high cost. So maybe we have to work on that. We can also do profile engineering like we did with the DJ LGAD, and at the same time improve integrated chip readout and do advanced integration. So for example, sensor to chip stacking of multiple layers. The key point here is we need to think what technology will be available in 10 years from now and start developing the tools to use them. So last little parenthesis on Blue Sky R&D that I've been doing. This is just one of the several projects that I've been following. So this is to apply LGAD, so this low gain avalanche detector for X-ray detection. So we went to the SLAC SSRL and we did one test beam last November, and we're gonna do another one in February. And we saw that this sensor, 2 minutes,
yeah,
okay.
2 more minutes, yeah.
Great, almost done. And we saw that this detector, they're great to detect X-rays, even at low energy, which is something that silicon cannot really do when you go to few kVs of X-ray energy. And we also saw that thanks to our detector, we could resolve every single pulse in the SSRL cyclotron. So every 2 nanoseconds, the pulse comes and goes. So you can see one pulse after the other. And with this sensor, we can have energy resolution 6 to 10% and time resolution of 100 picosecond. So thanks to these studies, we are starting to push this technology as beam monitoring technology for these kinds of facility. I've been collaborating with São Paulo. They're bringing up a very similar light source, and they are interested in using these devices as beam monitoring. So to conclude, first, a little parenthesis on what happened last year, which is NOMAS. So last year, since, again, we don't really know where we are going in the HEP field, we had this community planning exercise, SNOMAS, which allows us to gain some future visions of the HEP in the US and globally. And for this, I contributed to several white papers, went to the town halls, and I was at the final meeting in July last year. You can see me in the yellow circle. So the P5 report is coming out soon. That's based on the SNOMAS exercise. And I try to work hard to convince them that this timing technology is critical. And at the same time, also convinced that Pioneer is a really nice experiment to fund from the DOE side. So to conclude, there are dual but interesting times ahead because the breakthroughs can be unexpected. And as a community and also personally, it's a great time to look ahead. One crucial enabling technology that we need to develop is 4D tracking, and I've been working a lot on that. The first application is Atlas and CMS. That's we are gonna do Pioneer and APIC at the Electron Ion Collider. So I put a star there next to Pioneer because it's in my heart. I've been working on that since the beginning a few years ago. And this will probe the fundamental question of lepton flavor universality. And for this, we have this very, very advanced piece of equipment that we need to develop. So there are many challenges ahead in terms of precise 4D tracking, high radiation damage, and large occupancy, because we need to steer this development aimed at Higgs factories and future collider. So there was a great fast development of 4D detector based on the LGAD technology that makes them viable, as you see, as short, medium, and long-term application. And yeah, this is my last remarks, and thanks a lot for the attention. If you have any questions, please go ahead.
Right, thank you.
We have
guys can, as usual, speak up. Yes.
Okay, may I start again?
Sure.
Please.
Okay. Okay, Simone, also to you, thank you very much for this clear presentation. I have a couple of questions again. So the LGAD is for sure technology interesting, and many groups around the world are pursuing this and doing the R&D for this technology. So if you go to your slide 14, I want to ask you, since there are many groups working on this technology at CERN, BNL and stuff, I want you to clarify what exactly is your contribution on this, and also for the Pioneer experiment, what is your contribution? You are mainly involved on the hardware, or you have also some part of the software analysis, or so tell us a little bit more of your contribution in this context of the work that you have presented.
Yeah, absolutely. So first, let me start with LHC. So this plot, as you see here, it's all my work. Like these plots that went into the TDR that I was main editor of, I did it. So I collaborated with the companies producing these sensors. They get the sensor to UC Santa Cruz, then I test them, I mounted on boards. If you want, I can go into the details of how we tested these devices. And then organize the irradiation campaigns. We sent some to Ljubljana for neutron irradiation, some to Los Alamos for proton irradiation. Then you send them out for irradiation, they ship them back, and you test them again. And so you can do these plots and test the devices as a function of fluence. So this was my first contribution for Atlas. Then for Pioneer, if you look at one of these papers, basically this is the first paper where they talk about Pioneer and the ITER, and I am first author because the Pioneer experiment was started by the G-2 group and Pioneer group, that basically they contacted me when they had this vague idea of having this active target. I responded, they invited me in a conference, I gave a talk, and they're like, oh, are you interested in collaborating? I say, yes, this is really cool. And so basically I designed the detector from the ground up. I did some prototype demonstration by getting some old LGADs that I have lying around. I built up something, I tested them, I say, yeah, this might be possible. And now I've been working a lot in basically completely design this experiment from the ground up. And then at the same time, as I was saying, this deep junction LGAD is something that I hold a patent of. So I was talking with a professor a few years ago. We were bouncing off ideas like, oh, maybe we can build an LGAD with such and such doping concentration. And we had the idea, we ran some TCAD simulation, we saw that it was viable. Then we applied for funding through the SPIR program from the DOE. We got the funding, we worked with a company, we got the first prototype that kind of worked. Like you could see the gain of having the gain layer buried in. You can have more insulation on the pads, but it wasn't perfect. So right now I'm organizing another production through RD50 funds. This time with FPK, which is a company in Italy, to produce another batch of these sensors with also other ideas to make them radiation hard.
So mainly
I can go on if you want.
No, it's enough. If you go, so mainly for the DJ LGAD is the radiation hardness that you want to improve, while for the timing resolution is 20 picosecond is what stays the goal.
Actually, we want to go to 10 picosecond, which Yeah, 20 picosecond we can already do.
Okay.
I tested a few devices from Hamamatsu that can, I think the minimum we can do is 16 picoseconds. And 10 picosecond is the final goal, but it's really hard to get there. Like I've been trying in a lot of ways, and it's really hard to get to 10 picosecond. Another issue is the readout, because you can have the best sensor in the world, test them single pad on a great fast amplifier board. They give you 10 picosecond, and then you actually do an electronic chip to read them out when you have thousands of channels, and this of course screws up the entire time resolution. So it's really a complex program.
Okay, thank you. I think that I can stop here.
Emilio?
Yeah, so I wanted to ask a couple of things. I'm not familiar with what acceptor removal is, the damage mechanism you mentioned. So I was just curious if you could explain it a little bit.
Yeah, okay. So what happens basically is when you put a very high level of dopant in the gain layer.
We have some issues.
Problem.
You're frozen, Simone.
Is it
Simone,
better?
may I suggest that you turn off the video? Good.
Yeah, yeah. Can you hear me now? Is it better?
Yes.
Yes, I can hear you.
Yeah, sorry, I'm in a hotel now, so I don't have the best connection. So as I was saying, for normal silicon detector, the doping concentration in the bulk is something like 10 to the 14, 10 to the 13. And so usually the radiation damage issue for silicon detector is charge trapping. So basically they increase the doping concentration because of you have all this flux of particle coming in. But for LGADs, there is this initial acceptor removal effect. So when you have a very highly doped gain layer, you have a lot of boron inside the lattice of the silicon. What happens is that when something passes by, knocks off this boron, so it removes it from the lattice crystal, and this boron fuses with an oxygen, so it creates boron oxide. And what happens is that it becomes inactive. So you are actively losing doping concentration with radiation damage.
I see. Thank you.
Yeah.
And the other thing I was going to ask was in the active target for the Pioneer experiment.
Mm-hmm.
So what exactly are you focused on understanding besides the timing for the beam that's both incoming and then the decays that are happening in the target?
So the goal here is to actively see what happens during the decay. Because one big issue of pi nu, pan, pi beta, all this kind of experiment where they had a very good calorimeter, but then the target was just a plastic scintillator with no granularity, is that there is no way to tell when, for example, you get a positron in the calorimeter with 40 MeV, if it comes from the Mitchell spectrum or from the signal tail of the pi nu decay. And this tail comes from a lot of different factors. Like sometimes your electron comes out, it's 70 MeV, but then knocks off a little bit in between the target and the calorimeter, etc. And so it loses energy, and you have this large tail, or you have decays in flight, where basically the pion is coming in and then decays in flight into the positron instead of a rest, and the positron flies out in the other direction, and so it has less energy. So if you want to really get to the level of precision that we want, you need to be able to see this tail. And to see this tail, the only way is to have an active target that tells you, oh, something came in, stopped, and then you had another track out. Like all of these are eating the tracker. And this tracker is so compact that even though the muon travels for about 700 microns, you can have a few hits. And you can tell that those few hits come from a muon because they have a high energy deposition. So this is kind of the situation of how we want to see the two events, to tell the two events apart. So one case comes in, stops, and comes out. In the other, comes in, stops, another track stops, and then the electron. And then the complex decays in flight. We have to think of smarter way to detect them, but it's still possible because this device is very granular.
Okay, so spatial resolution of energy deposition.
Yeah,
so that you
spatial resolution energy.
And the timing, I
the
didn't
other thing is...
Yeah, so why do you need the timing? Is it to separate between incident particles? Like from...
Yeah, so the timing helps you between, to suppress the pileup, for example, in the Calo, because the liquid xenon Calo can give you something like 100 picosecond of time resolution. So if you have good timing of this exiting positron track, you can say, okay, at the same time, so you can match them. And the other important thing is, more than the timing, is the ability to go back to baseline very fast. So if you remember when I showed the... Okay, sorry.
Yeah, I think we are running out of time and we should move on to the next speaker.
Okay, sorry. Yeah, I talked too much about my research.
You're just fine. Thank you.
Okay, good. So the last but not least, Chiara Trovatello from Columbia. And Chiara, the floor is yours.
Thank you very much. I hope you can hear me and see the screen.
Yes,
both. Right. So the meeting control and also the video panel. Okay. Great. Thank you very much. It's great to be here. I'm very thankful to the whole committee for giving me the opportunity today to present my research. Before diving into physics, I just want to give you a little background of myself. I was born in 1992 in Syracuse. It's a beautiful city in the south of Italy, probably best known as the city of Archimedes, where he was born. So Syracuse was a Greek colony, so full of history, extremely rich in history and cultural heritage. But beyond that, we also have incredible landscape and incredible seaside. So this is one picture I took at our nature reserve, and this is me feeding some fish underwater. Here, people cannot fish, so the animals feel really safe. You can cuddle them, you can you can feed them from your bare hands. It's actually a pretty cool experience. But as all good things come to an end, in 2011, I had to move to Milan for my studies in engineering physics and also my PhD in physics that started in 2016. So during those years, I really dived into the topic of photonics. Broadly speaking, I worked with the generation, detection, and also manipulation of light. And specifically, my expertise focused into the field of nonlinear optics, which is essentially a tool that allows us to create new colors of light, or in more technical terms, new classical and also new quantum states of light. So I'm going to start briefly introducing nonlinear optics and ultrafast spectroscopy. So how can we understand nonlinear optics? If we take a material and we excite this material with a very intense optical field E, the response of the material, which is the polarization P to our external excitation, can become a nonlinear function of the field. So you see that the polarization is essentially, in the polarization, this higher order nonlinear terms start appearing. So the susceptibility, which is a property of the material, shows up in the second order, third order, and so on and so forth. So starting from the simplest nonlinear optical effect, which is second harmonic generation, here we can sum two photons at frequency omega and get one photon at frequency 2 omega. But you can also sum two different photons, for example, omega 1 plus omega 2, and get a third photon at frequency omega 3. And you can also subtract the two photons. You can make, for example, omega 1 minus omega 2. And this is called difference frequency generation. So if we do omega 1 minus omega 2, you get this omega 3 photon, which is the difference. But if this happens due to energy conservation, you also amplify the field at omega 2. Here you see we had one photon, at the output we have two. So difference frequency generation also underpins the so-called optical parametric amplification. And last but not least, spontaneous parametric downconversion is also one nonlinear optical effect in which we take one high energy photon and we split it into two lower energy photons. So nonlinear optics is a great tool. It allows us to make mathematical operations with photons in the end and to generate both classical light and also quantum light. In fact, spontaneous parametric down conversion is one of the ways, for example, we produce entangled photons for quantum computing and quantum information. And this is how it looks like. This is basically this has been my morning routine throughout my PhD. This is how an OPA looks like, an optical parametric amplifier. I'm calling the omega-1 and omega-2 the pump and the signal photons. The idler is the frequency difference, and at the output we have this very intense green spot, which is the amplified signal shown here in the piece of paper. Just to give you an idea of how big these nonlinear crystals that we use to generate these nonlinear effects are, you can see pointed here, it's a pretty bulky object. It's on the order of a few centimeters. And I'm playing with mirrors, so you see the size of the OPA. But why is OPA so important and has been really a game changer in spectroscopy? Because it has really allowed us to tune the color of the laser, which is typically only one wavelength, only a single color, into powerful laser light at any color. And for spectroscopy, for example, it's crucial because it has enabled us to explore the optical response of matter at different light colors. So this is what we do when we do probe spectroscopy or ultrafast spectroscopy. We have a laser source. We split it into two beams. One is the pump and one is the probe. The pump photoexcites electrons, and then the probe monitors this electronic relaxation back to the ground state. And in fact, it's a pretty powerful technique. We can track photoexcited electron dynamics in the visible range down to 10 femtosecond temporal resolution, which is basically the limit, the intrinsic limit that we have. And just to remind everyone, 1 femtosecond is 10 to the minus 15 seconds. So it's really an ultra short flash of light. So during my PhD, I focused on the topic of ultrafast spectroscopy. I played with nonlinear optics to build setups of ultrafast spectroscopy to study two-dimensional materials. So probably you're familiar with graphene. Graphene is a prototypical two-dimensional material. It's carbon in 2 dimensions, and it was worth the Nobel Prize in 2010. And it's a 2D semi-metal, which means if you look at the band gap of graphene, there's no band gap. The conduction band and valence band touch at this point. But similar to graphene, there are also other compounds in the family of 2D materials, like transition metal dichalcogenides or TMDs, which in contrast with respect to graphene, those are 2D semiconductors. You see there is a band gap. And these are compounds in which we have a metal sandwiched between two chalcogens. So we can form compounds like MOS2, MOSD2, WS2, or WSC2. These materials have really changed the history of physics because they have introduced new functions and also new applications into this world. So this is a one-slide summary of my PhD. I tried to answer very basic questions regarding the photophysics of these materials. For example, how quickly electrons and holes get bound to form excitons in these 2D materials. What is the role of optical phonons in the ultrafast exciton relaxation? What happens to the optical band gap when we photoexcite a 2D semiconductor? Or if we take, for example, graphene, which is a 2D semi-metal, and we put a 2D semiconductor on top, how fast is charge transfer between these two materials? But towards the end of the PhD, which is also the main subject of my postdoc research, we tried to basically use these two-dimensional materials not just as subject of ultrafast spectroscopy studies, but we tried to use 2D materials as nonlinear crystals itself. So to make nonlinear optical effects inside these materials. For example, I was showing this optical parametric amplifier, and I mentioned the thickness of these crystals. They're pretty bulky, pretty macroscopic, thickness on the order of millimeters, even centimeters. So can we substitute these bulk crystals with a 2D material? Of course, a 2D material is less than a nanometer thick, so we're talking about totally different spatial scales. But if this is possible, we could effectively realize the thinnest possible optical amplifier ever. And if we look at the numbers, if you compare the standard bulk nonlinear crystals that we currently use in our labs, like BBO or PPLN, the nonlinearity of this crystal is pretty small. It's 10 to the minus 12, 10 to the minus 11. And if you look at these two-dimensional materials, the nonlinearity is huge. It's 10 to the minus 10, 10 to the minus 9. It's basically 3 orders of magnitude larger than BBO. So we did it. We amplify light at the nanoscale with an atomically thin material that was cool. And as you can see from this plot, the amplifier works basically tuning from across the all visible range, which was pretty powerful. So at this point, you might ask yourself, okay, great. So we can just throw up all these bulk nonlinear crystals and use 2D materials from now on. Unfortunately, this is not possible yet, in the sense that the chi2, so the intrinsic nonlinearity, is not everything. If you look at the efficiency of these crystals and you actually compare, for example, for second harmonic generation, which is the simplest nonlinear optical effect, the intensity of the second harmonic is not just dependent on the nonlinearity chi2, but it depends on the product of the nonlinearity square times the thickness square. So if you compare BBO and crystals, classical crystals like PBO, PPLN, which have a millimeter or even centimeter thickness, you can really get a high gain, despite the fact that chi2 is pretty small. But if you compare two-dimensional crystals that have a huge chi2, the gain that we get is actually very, very small, something like 10 to the minus 11, 10 to the minus 10. Okay, compared to the commercial crystals that are 10 to the minus 2 or 10 to the minus 1. So 10 orders of magnitude, almost lower efficiency. So how can we bridge this to macroscopic and microscopic nonlinear optics world? Because TMDs have potential with this extremely high nonlinearity. So here I'm going to discuss ideas to increase the nonlinear efficiency of two-dimensional materials. So the first thing that can pop up to your minds is, why are you using monolayers? Why don't you just use thicker crystals so your gain gets higher? But it's not a trivial answer to the problem, because if you increase the number of layers, the crystal structure of these TMDs, these 2D materials, really matters. So for example, there are two crystal structures. If you use the 2H crystal structure and you increase the number of layers, the chi2, so the nonlinearity, is equal to 0 because the crystal symmetry changes. So this is not really a good crystal phase to use. But if you use the 3R phase, which is always chi2 different from 0, people have shown, in fact, that if you increase the number of layers, you can increase the second harmonic generation and up to, for 6 layers, 36 times, because this scales as the thickness square. If you remember, I was showing this a few slides ago. And in fact, if you look at this conversion efficiency of these materials versus the thickness for monolayers, which is less than a nanometer, we convert something like 10 to the minus 10 with a few layers. So let's say 5 to 6 layers, we are up to a conversion efficiency of 10 to the minus 8. So how can we increase the number of layers even more? Can we go to 10 layers, 20 layers, 100 layers? There's a bottleneck here. And the problem is that when you open textbooks and look at the dependence of the second harmonic versus the thickness of our medium, you have this oscillating curve. And the semi-period of this oscillation is called coherence length, which means basically that we measured this coherence length in our 3R samples. And you see this is on the order of 500 nanometers telecom wavelengths. Great. So what do we do with this value? Basically nothing, because if we keep increasing the thickness, you see this oscillates. So where does this come from? This comes from the fact, that second harmonic and pump inside the crystal basically travel at different speeds. So when they go in phase and then out of phase again and in phase again and so on and so forth. And so you don't really gain much doing this. But what is good about this plot over here, beyond reporting for the first time coherence length, is the fact that the TMD at the thickness of about 400 nanometer was showing a second harmonic 10 to the 4 times stronger than a monolayer. So this was pretty impressive and pretty high. But the problem here is that this dephasing is caused by the fact that there was no phase matching in the crystal. So how do we get even higher efficiency? Increasing the thickness just doesn't work. We have to engineer the crystal and engineer the optical properties to get the so-called phase matching condition. So if we get phase matching, you see when you increase the thickness, this scales quadratically with the thickness of the medium, and we can have high efficiency. So in this plot, with one single bulk of 400 nanometer, we reached 10 to the minus 6 conversion efficiency. Can we boost this even more? We can do this achieving phase matching. So this is the last part of the talk, where I basically describe the final goal of the whole project, which is trying to bridge these two worlds.
2 more minutes.
We did it. Thank you. This is the last slide. So we did it. We engineered the crystal at the nanoscale. We were able to get, with a 1 micron thick object, a conversion efficiency of 10 to the minus 4. I cannot really disclose right now the way we engineered the crystal to achieve phase matching, because we are in the process of patent protecting this idea. But what I can tell you is that this crystal, despite being extremely thin, so not even close to a millimeter or a centimeter thick, this is a micrometer. It's so bright that you can see it by eye. And on top, you see a picture taken with my phone of this light, second harmonic light produced by this tiny crystal. And at the bottom, you see this frequency tunable second harmonic generation at all different colors of the visible spectrum. So we are really bridging these two worlds, and we are kind of disrupting this trend of the thickness versus conversion efficiency. We're now getting to the value of the efficiency of commercial crystals, which are millimeter or even centimeter thick, by using a crystal that it's only a micron thick. And this is pretty exciting. This has been basically the content of my research as a postdoc here at Columbia. Everything started from the OPA with monolayer done in 2019 when I was visiting PhD here, and this continued the work. Actually gave the name also to the Marie Curie Fellowship, which stands for phase match nonlinear optics in layered semiconductors, and also gave the name to the talk today. Last thing I want to mention, during my PhD, I was founder and former president of the student chapter of Milan. This was a great opportunity for me to advocate for scientific outreach, open science, equal opportunities, and equal representation in STEM, and I'm very grateful, and I wanted to mention this. With this, I conclude. What's next step? I mentioned at the beginning, we could generate quantum light. This is what we want to do with our crystals, and hopefully generating entangled photons on a chip. This is still a dream in the world of quantum computing, in the world of integrated optics, and we believe with these extremely thin crystals, we'll probably make it. Thank you very much for listening. Thank you to the funding agencies, all the people contributing to this work, especially my PIs, Giulio Cerullo, Stefano Del Conte, and Jim Schock, for continued guidance and inspiration. Thank you very much for listening, and I'm open to take any questions.
Thank you again. Thank you. And maybe, I don't know, maybe we go the same way at this point, if Patrizia has something.
Yeah, I'm I have to collect my, there are a lot of things very interesting. It's not my field, so I see that I was trying in your second to last slide to see, okay, but then what is the advantage of having the same, go at the end, sorry. Or end of your presentation, you don't have the number of the slide here. Yes, this one, no, the previous one, yes. So I was, but then you answer. So you want to have the same characteristic of your medium with a much thinner layer. So going to millimeter to microns, and you show at the end what could be a very interesting application for this. One thing is, for instance, on the quantum computing. Do you have already some interaction or exchange with people working in that field to see what kind of needs they have and in which way you can tune your research?
Thank you very much for the questions. Yes, correct. We want to reduce the footprint, essentially, of these bulk crystals to make them on a chip. And we have some contacts with some companies, as well as some people in academia. So, for example, for this project, we're collaborating with a group in Vienna, actually the group of Philipp Walter, which was a former PhD student of Anton Zeilinger that got the Nobel Prize for quantum optics a few years ago. With them, we're working on the quantum measurements. So here at Columbia, we're engineering the crystals and then measuring them in Vienna to measure all the quantum measurements. With them, we're also trying to engineer the crystal in such a way that we actually have advantages. So the first advantage is the size. Now people do entangled photons outside their chip. They couple the entangled photons on fibers, and then these fibers bring the photons on a chip. This is intrinsically a very lossy way of doing this. So if you could in the future put the source directly on the chip, this would reduce the footprint of the device. Basically, the old chip would have the size of the one crystal that now makes just one source of photons. So this is the first advantage. And also you can play with entanglement due to the fact that the dimensionality is reduced here. You have entirely different properties compared to the bulk crystals in terms of like polarization entanglement or energy time entanglement and so on and so forth. So there are a few directions that we are working on. I don't have any results to show yet, but I can say we're confident that soon we're gonna have some interesting new results to show on this side.
Very interesting. Sorry, if I can just follow up on that. I was thinking while you were talking that maybe also a great application could be in the medicine. So in a hospital, if you want to have tools that has a very low dimension to be less invasive, I don't know if this could be also a direction that you are thinking about.
Yes, absolutely. This is a great point. Actually, on this sense, for example, lasers, the size of lasers is that big because the crystals inside are huge and the way you build the cavities inside are huge. So with this crystals, technically, you can also reduce the footprint of lasers. So take your tiny laser, bring it to the hospital, couple to a fiber, and maybe do some even in vivo measurements. So this is also something that we can think of. Yes.
Okay. Thank you very much.
Thank you.
Chiara, very, very, very interesting research.
Yeah, yes, Chiara, very nice. Oh, Giorgio, do you have a question?
No, I mean, we're going around the usual way. So at this point, it's your turn.
Okay. So I was, yeah, very nice talk. I guess my first question is you discuss a lot about like integration with photonics on chip. Any thoughts on how to actually do that integration from like a bonding or a nanofabrication perspective?
Thank you for the question. We are working on patterning the crystals first and then transferring the pre-patterned crystals on a silicon nitride device, for instance. It's something we're already working on, collaborating with the Lipson's group here at Columbia, with the Oselames group in Milan, and also with the company FBK in Trento in Italy. So there are some ideas. Right now, the most challenging part is actually the refractive index mismatch between the silicon nitride platform and this high refractive index materials. Due to lack of time, I didn't mention this, but the high refractive index of this material is like double the one of the silicon nitride. So intrinsically, you have losses and reflections. So right now we are trying to optimize first the coupling in the TMD and also the coupling out. This is not trivial. We have to do directional couplers. We have to think of many different on-chip platforms and components inside the chip to work on. But it's something we're working on right now. So I would say to answer directly your questions, two things: characteristics of the base circuit that comes typically from a prefab. It's prefabricated from a company, and second, how to optimize the coupling from our perspective. So nano engineer and pattern the crystal to match the waveguides and all the resonators and the elements on the chip.
And how does the Chi2 vary as a function of like whether you're perpendicular to the surface of the monolayer or in the plane of the monolayer?
Really good point. Actually, we don't have a number for the out of plane Chi2. Simply because it's at the moment very tricky to go with fibers and enter from the sides of the flake because it's extremely small. So there's no
like if it's
quantitative
bonded, for example, to a photonic waveguide, you could then interact through it.
We could. That is true. But consider that the size of this overall is like maybe tens of microns. Yes, so we're not talking about like, yeah. So like, that's one option. Also, the sidewalls are critical because you have to characterize how much light you couple in and you couple out to get a number for Chi2. So
I'm the timekeeper. I'm really sorry. I just want to mention that we are running out of time. So
thank you.
You bet.
Okay. So maybe since we are running out of time, I will refrain from making, like I also did the previous time, I'm kind of refraining from making my question, although I had some question about super radiance, but I guess well maybe we can do it offline. Okay, so I think this is probably the end of our program. I see Patrizia and Cinzia nodding, so presumably
Yes.
not saying anything grossly wrong.
No.
So I think we should really thank
No. Just a moment, Giorgio.
Oh, okay. Yes. Cinzia,
Sorry to jump in. Just a word from your friendly president of ISNAF here. It has been a great series of presentations, right, with such energy and command, really enjoyable. But I just wanted to go 1 minute longer because in the audience we have Maurizio Biasini from the Embassy of Italy in DC, the scientific attaché. He is also a specialist in the subject matter. He is close to INFN, which is our sponsor for the event. So we are really grateful here to INFN for making it possible for these people to be here tonight and have a chance to have their great work recognized. Maurizio, I wanted to leave you the floor for a moment to help us thank them as well. Maurizio, are you there?
I need authorization. Okay, now I can do that. Still, I don't think you can see me because I'm not authorized to turn on the video, but I can talk at least. So I don't want to take you most of the time, but thank you, Cinzia, for allowing me to bring the greetings from the embassy. Thanks to the members of the jury for selecting such brilliant young researchers, and moreover, congratulations to the 3 finalists who, despite their young age, they have such already a deep experience, I would say, and very nice way and clear way of presenting their results. Of course, physics is one of the main areas of collaboration between Italy and US, and sorry, yeah, but it has been changed now, my settings, and now allowed to be. I hope that you can see also me. I will say that physics is, of course, one of the main areas of collaboration between Italy and US. And this was deeply discussed during the last meeting, which was held in Rome, the Joint Commission meeting, which is the meeting discussing the area of interest in science and technology cooperation between Italy and US, since an agreement exists in 1988 between the 2 governments that decided to cooperate in this field. And every 3 years, the area are discussed, and the focus area for the main subjects for the coming 3 years. And of course, physics and astrophysics was included again for the coming 3 years. And then it was thoroughly discussed also in bilateral meetings between INFN, Department of Energy, and National Science Foundation. Agreement exists between the Ministry of University and Research and Department of Energy and National Science Foundation, stating that there is an interest also at the national level in this field of research. Of course, the network of Italian researchers abroad are an essential part and component in what we call the Sistema Paese, the action to try to promote our country abroad in terms of bilateral cooperation in different sectors, of course, from economy to culture, science, technology, innovation, which is our subject. We science attaché at the embassy are trying to support this cooperation. And in particular, we support ISNAF in many ways, for example, sponsoring an award. And I think that in the next meeting, you will listen to the finalists for this award. And also, as Cinzia mentioned, trying to promote the possibility of new awards, like in the case of Bruno Touschek Award, which is sponsored by INFN since last year. In addition, we organize and support the organization of the ISNAF annual event here at the embassy, So I just want to conclude, say that I hope to see all of you here at the embassy, and I'm looking forward to meet you here in person for the annual event of ISNAF. Thank you. Congratulations again for the organizers, but even more for the 3 finalists, which I'm really happy to have the possibility to meet in person here in Washington. Thank you.
And with this, thank you all. I think now we can close the event. Congratulations again.
Thank you. Thank you.
Bye.
Thank you.
Thank you.
Bye.
Bye-bye.
See you soon.